Johnston Island was the center of launch and experimental activity for the 1962 high-altitude weapon effects testing termed Operation Fishbowl, geared to collect effects data from nuclear bursts at high altitudes. Standing offshore were 9 instrumented test ships, vital links in the Fishbowl effort. On islands south of the equator, in Johnston's southern magnetic conjugate area, a variety of instrumentation to collect effects data was set up for Fishbowl. All in all, of the 266 Fishbowl instrument stations, 156 were on land, while 10 ships housed 80 separate project stations. 15 test aircraft carried the other 30 stations. The need for the test work carried on at Johnston and its far-flung array was compelling, for it stemmed from urgent Department of Defense operational needs requiring that high-altitude phenomena resulting from a nuclear burst be defined with simultaneous direct measurements on military operational equipment. For while America had been making rapid strides in other aspects of missile technology, its investigation of high-altitude nuclear detonation effects had lagged due to the 1958 test moratorium imposed shortly after the nation's first look at nuclear effects at high altitudes. From a ship in the South Atlantic, 3 small detonations, known as the Argus series, were launched and triggered aloft for the purpose of examining the Christophilus theory that a long-lived belt of trapped electrons could be artificially created by a very high-altitude nuclear explosion. Other effects on Argus, although measured, were not thoroughly documented. In the Pacific, as part of the hardtack series, 3 effect shots, Yucca, Orange, and Teak, were detonated at respectively 26, 43, 77 kilometers, primarily to provide information on the change of blast, nuclear, and thermal effects with increasing altitude. From hardtack's limited test experimentation, one lesson learned was that widely diverse quantitative effects were produced at different altitudes, including major electromagnetic disturbances, causing communications and radar blackout problems. The nature of each effect could be learned only by actual testing. More than the information they furnished, these 1958 shots indicated how much more there was to learn about nuclear burst-created atmospheric ionization. One objective concerned ICBM acquisition, tracking, and intercept problems. It was essential for both defensive and offensive planning that experimental data be obtained on the effects of high-altitude nuclear bursts on radar performance. A third objective concerned communications blackout, that is, the loss of signals due to disturbances in the ionosphere caused by high-altitude detonations. It was necessary to know the ensuing effects on military command and control systems which require long-range communications. These military objectives meshed into the overall Fishbowl objective of gaining a vertical scale of information for various altitudes and yields. Included in the wide assortment of Fishbowl projects were thermal studies on I-burn, investigation of debris distribution, and documentation of the nature and transport of the magnetic field disturbance generated by high-altitude detonations. On Operation Fishbowl, nuclear detonations rent the sky 5 times over the Johnston Island area, each time during the hours of darkness. Of the 5 Fishbowl shots, the highest burst was the 400-kilometer Starfish event, launched by a pod-carrying Thor missile. Its yield was 1.4 megatons. In addition to the local phenomena, the transport of bomb debris and other charged particles in the magnetic field produced colorful aurora, arcing into the northern and southern conjugate regions. Checkmate, like Starfish, did not display a well-defined fireball. Checkmate exhibited a moderate aurora seen in both the northern and southern conjugate areas. Kingfish's fireball was well-defined and its aurora moderate. Refraction effects from a nuclear burst are of concern in the high-precision target tracking of ICBMs in the terminal phase. Although radar on the damp ship and Johnston Island showed no gross refractive effects from any of the bursts, preliminary results indicate a refractive jitter problem under certain conditions, involving a rapid fluctuation in the apparent angle of arrival of returning radar pulses. It was present on all events, but most pronounced on bluegill and kingfish. Another electromagnetic effect important to DoD's search capability is clutter, which could hamper radar performance for a period longer than other effects. Radar clutter is caused by ionized air, ionized bomb debris, and electrons trapped in the magnetic field. All these materials reflect radar energy, giving rise to false targets on the radar scope. Our first consideration is the reflection clutter from the fireball itself. Confined to the visible fireball, it is most pronounced when a well-formed fireball is generated. Another problem is presented by field-aligned clutter, observed in that region of the sky for which the observer is at right angles to the magnetic field lines at E-layer heights, and within an azimuth of about 15 degrees to either side of magnetic north. Of the serious electromagnetic effects from the burst, least bothersome to radar performance is noise. Highly sensitive advanced radar systems are adversely affected by the detonation's broadband radio frequency noise, since it reduces the signal-to-noise ratio. In the high-frequency experiments, burst-induced ionization altered propagation conditions, but caused no widespread outage. After the detonation, usable frequencies tended to be higher than pre-burst values. On some paths, propagation conditions were enhanced by the creation of new modes or paths. Almost all conditions had returned to normal by H+2 hours, except on Starfish, where effects were detectable Pacific-wide for 2 days. Checkmate caused some adverse effects on transmission paths within 700 kilometers of Johnston Island for about 30 minutes. Kingfish altered propagation conditions on paths within 2,500 kilometers of the burst point, as well as throughout the southern conjugate area for several hours. Bluegill caused blackout for about 1 minute of certain high-frequency signals whose paths passed within 200 kilometers of the Johnston Island area, with lesser effects observed on these paths for 2 hours. Tightrope produced no observable propagation changes. VHF and UHF communication circuits were not degraded by the high-altitude events. Encouraging results were obtained from a strategic air command experiment, testing its airborne communication system during several high-altitude nuclear bursts. Signals from an UHF transmitter on Johnston Island were received by a KC-135 aircraft in the area and retransmitted to a relay B-47, which in turn retransmitted the signal to Hickam Air Force Base. Communications were not disrupted on this circuit by the high-altitude events. The optical measurements documented the spatial, temporal, and spectral characteristics of UV optical infrared effects associated with the detonations in the burst area, as well as the southern conjugate region.